So I will now go. Where are my slides? I lost my slides. Where are my slides? Here they are. Slides. No. Here they are. Okay, sorry, you can't see what I'm doing, but I was a bit lost. So, we are now playing around in chapter 3 with an important family of processes which are called ARMA processes. And I think it's useful for me to do, it's not really a summary, it's just I'll go back over everything that we said last week. Hopefully you have read the chapter, or at least tried to read the chapter, and hopefully you've asked yourself a few questions, and I will now, yes, I think the record is on, yeah. Well, hopefully I'll be answering, maybe I'll be even answering some of your questions, Clara, by this summary. So when I was preparing for today, I realized that it might be useful to go over all this again. And I'll do it by hand this time because it goes a bit slower by hand and it might be a bit clearer. So I will share, no need to write what I'm writing, I'm just going to be saying what's on the slides, probably slightly differently. And I will of course share with you these notes at the end of the class, so you will be losing nothing. So, the first basic definition is that of an ARMA PQ process. And we say that a stochastic process indexed in time is ARMA of orders P and Q if xt is a stationary solution to yeah, Yusuf, it's on, don't worry. There, you see, it's moving. Is a stationary solution to the ARMA equation, which I think I prefer writing like this. Phi of b times xt is theta of b times zt, where zt is in a white noise sequence. It means 0 and variance sigma squared, and phi of z b of process is just the backwards operator, and phi of z is the autoregressive polynomial, which we decide to write in this form. So this is the autoregressive polynomial, and theta of z is this polynomial here. And that's the moving average polynomial. So that's the basic definition. Maybe one computation I did a bit fast, I want to do it again. It's the first one that said that if xt is a stationary solution to equation which I will call 1. Are you okay for reading what I'm writing? It's okay? My writing is awful, but I guess you get used to it. Nobody's complaining, that's good. So if xt is a stationary solution to 1, then what? Then what do we know? We know that the mean of xt is constant, because it's stationary. We call it mu. and it must satisfy, well, if you look at the expectation on this side here, what you're left with 1 minus phi 1 minus so on minus phi p, because it's just expectations of so it's just expectations of xt's at various times. So this multiplied by mu, and this has to be equal to the expectation of this guy, and all these guys are stationary with the mean, where is it? It's here, with mean 0, so this has to be equal to 0. So this tells us what? Well, it tells us that well, either the sum of the coefficients of the AR polynomial have to be equal to 1, or mu has to be equal to 0. And typically we take mu is 0. Another definition is that xt is arma pq with mean mu if xt minus mu is arma, so this would be definition 3.2. And then let's say that this is definition 3.2 prime. Xt is arma with mean mu if xt minus mu is arma pq, as in definition 3.2. So this is things that we discussed last week. I think the rest is more or less clear. So then we had section 3.2, which was discussing special cases. And the two special cases we discuss are, on the one hand, the moving average of order q. So this is the case where it's purely moving average, so there is nothing here, only the constant 1. So the polynomial theta is the moving average would be the case where the polynomial phi is equal to 1. So on the left hand side we have 1, and then this is whatever it is. And the second special case that we are going to spend some time with is the case of a purely autoregressive process for which we have theta of z, which is equal to 1. This means that nothing is happening here, we just have the noise at time t, so we just have 1 here, and all these coefficients here are 0 and disappear. Okay, so the first one we concentrated on was the moving average. In this case, it has to be a stationary solution to this very simple equation, which is the following. There is no problem of existence for such a polynomial because the zt, the white noise, is a sequence that exists. Once we are given the white noise, we simply define xt at all times t as this linear combination of the white noise. So there is no problem with the definition. Stationarity of the solution, existence of a solution to this equation is, in this case, trivial. Stationarity of this solution is, and it's something I'm not going to do again because I really think it is easy. So it's easy. So I put guillemets to show. Again, I insist, please be able to do this. Without looking at the exercise solutions. CTP1 if you want to have an exercise sheet number 1 if you want to have the detail of the computations. And what do we see? Well, we see that the expectation of this guy is necessarily equal to 0, and the covariance of xt with xt plus h does not depend on t. It's a certain function gamma of h which is nicely even, and it's going to be given by this expression here. So this you have to be able to do. So that's the case of the moving average. The autoregressive of order p is given by this equation here. So phi of b xt is supposed to be equal to zt, which is the same as xt is phi 1 xt minus 1 plus plus phi p xt minus p plus zt. So first remark is that be careful with the literature or with your software for the interpretation of the phi j's. I mean that in certain cases the phi j's will be so in certain software the phi j's that I write here are in fact the opposite of the phi j's that are encoded in the software. It really depends on the parameterization chosen. It changes nothing in practice, but for the detail, if you're starting to work with well, just you have to be careful of the parameterization in which you're working. That's all I'm saying. Second is that it's really hard to check existence. For general parameter combinations. And we won't prove a general result. I will give you one, but I won't prove it. So we decided, well, I decided for you that we would focus on p equals 1. A very easy thing for me to do for the exam would be to focus on p equals 2, for example, or something else. So I ask you to work with a specific combination of parameters. It makes for a very simple question for me, and it makes me check. It's easy for me to check if you understand what's happening. So this is an example. It's not an assurance. I'm not saying that I will do that, but I could do that. Okay, so in the case p equals 1, what are we left with? Well, we're left with the equation xt is phi 1 xt minus 1 plus zt. I call this equation star, and there are 3 cases. Case 1 is when phi 1 is an absolute value less than 1. Case 2 is when phi 1 is equal to 1. And case 3 is when phi 1 is larger than 1 strictly. Okay, so the first case is again basically covered in the notes, so I'll go quickly over this one. In this case, while we do it's very similar to what we did in chapter 2, page 8. We start with this, then we work recursively to decide that for every n we can write this. We call this guy xtn. This guy here is some form of remainder. And because phi 1 is less than 1, the remainder goes to 0 necessarily in any possible way that you can imagine. Goes to 0 as n becomes large. And we show in the notes that xtn, so this finite combination of these factors here, converges in L2 and to this process here. And we also so that if a stationary solution exists, if a stationary solution exists, it must be given as, well, the L2 limit of this, so this infinite series here, where we look at this infinite series as its value in an L2 limit. And then what did we do? We did, so given this, I'll let you check it, but it's given in the notes. What did we do? We checked that. So given this guy, given this process, we check. So that's on page 9. That it is solution to equation star. So to this equation here, by checking the limits, and we use proposition 2.9. So proposition 2.9 is a proposition which gives you a case in which you are allowed to exchange limits and expectations. So this allows us to justify that, well, first of all, xt is indeed the L2 limit as n goes to infinity of this process, this finite sum here. Secondly, that the expectation of xt is then equal to the limit as n goes to infinity of the expectations of the xtn's, which is then 0. And then thirdly, that the covariance of x is I'm not doing this well, like this, it's going to be better, is indeed a function which does not depend on t, which is equal to the limit So this is like this. No, that's not well written. I want to write like this. So again, by proposition 2.9, we justify that we can take the limit out of the scalar product. There's a h missing. Like this. And well, it's not hard to compute the covariance of xt_n with xt plus hn. This guy is equal to this expectation here. So I'll try not to make any mistakes. So this is this, and I multiply here with this sum here. So I change index, just not to get mixed up, like this. Now this obviously is equal to this expectation here. Now this is a finite sum, so these guys can come out. Oops. Like this. Sorry. This guy can come out as well. Like that. And now we know that this is, because it's white noise, we know that this is equal to 0 if t minus I is not equal to t plus h minus j. And it's equal to sigma squared if t minus I is equal to t plus h minus j. So this is equivalent to what? It's equivalent to saying that j is h plus I. I think that's correct. And then if we just concentrate on j's which are equal to h plus I, well, we will be left, so it's not really a double sum, it's only a single sum. So we're left with the sum for I going from 0 to n minus h, otherwise we have nothing to sum. Phi 1 to the power 2i plus h times, well, now times sigma squared. And this tells us what? It tells us that if we go back into here, it tells us that the covariance that we were trying to compute at the beginning is equal to this. And this one can come out, and this one can come out as well. And this limit here is equal to 1 over 1 minus phi 1 squared, which we know is the case because phi 1 is less than 1 in absolute value. So that we're left with what was announced, which is this. So, conclusion of this little piece of work. Conclusion. In the case of an AR1, xt is equal to phi 1 xt minus 1 plus zt has a unique solution in L2 given by xt is the sum, wait, I'll put this down here to give you a nicer PDF afterwards, given by this sum again it's the L2 limit, which is sorry, I'm not entirely correct here. So it has a unique stationary solution given by this with, well, with mean 0, and with covariance, which is well, this covariance is a function which is never 0. It's a function which looks like this. So if, for example, if phi 1 is positive, it's going to be something that goes to 0 like that, slowly. And if phi 1 is negative, it's going to be oscillating depending on the sign of phi 1, but it will also be going down to 0, well, exponentially, I meant to say. So far, okay for everybody? I guess that's a yes. So that was the case of phi 1 less than 1. Oops. The next case that I went over a bit quickly is the case phi 1 equal to 1. Now, if phi 1 is equal to 1, the corresponding process is what? Well, xt is going to be so xt is xt minus 1. Well, yeah, it's plus or minus xt minus 1 plus zt. It's therefore well, yeah, to fix ideas, I'll take phi 1 is equal to 1. If phi 1 is equal to 1, then xt is just xt minus 1 plus zt. It's therefore xt minus 2 plus zt minus 1 plus zt. And I can continue like that. Let's say I only look at t which is positive. Then I can go down to x0 plus what? Well, plus the sum for j going from I think there's a typo in the notes. It's j going from 1 to t of the zt's. Yeah, and I wrote a 0 there, which, well, then it should be x minus 1. And this is what? Well, that's a random walk. And it's not stationary. So it's well defined. The solution is easy to identify in some sense. We just have to take this process here for a t larger than 0. So we fix some x0 and then we take the process which is here. But it's not stationary, therefore in fact not ARMA, because ARMA is supposed to be stationary. Now, to check that it's not stationary, maybe it's useful to do it, so please be awake. So expectation of xt will be the expectation of x0 plus 0, because the zt's are white noise, and let's say that it's 0. That's my choice. I decide that I want to take expectation of x0 is 0. And then what? Well, then with this in hand, the expectation of xt.
Professor?
Yes?
Plus sum of z t minus g, no?
Sorry, you're right. Sum of z j. Thank you.
Z g. Okay,
Yeah,
thank you.
very good. Yeah, and I had written z j. Yeah, of course, you're right. Otherwise this made no sense. So yeah, we're summing all the increments up to order t. So expectation of xt. So thanks again. Xt plus h. I now replace by the definition. I'm left with this. I put I put a J here and an I here. Sounds reasonable. And I simply develop this now. I will be left with what? Well, I'll be left with the sum here squared. Not squared. This sum here. It's not t, it's t plus h. Let's say h is larger than 0. T plus h. And then I'm left with this multiplied by this and this multiplied by this, but because we suppose that xt only depends, xt is a function of the past only and the zt's are uncorrelated, x0 is uncorrelated with this guy, x0 is uncorrelated with this guy, so that we're left with 0, and then we're left with the expectation of x0 squared. And this is what? Well, that's quite easy, because this is the expectation of let's say z1 up to zt multiplied by z1 up to zt oops, sorry, like this, plus zt plus 1 up to zt plus h, like that, plus this guy. And now I get this multiplied by this. Well, that will give me just a nice sigma squared times t. And then I will have this multiplied by this, but because they are uncorrelated, it gives me 0. Like this. So I think I made no mistake. And this is not independent of t. So it's not stationary. Okay with this? So that's the case phi 1 is equal to 1. And then, yeah, I'm wondering if any of you tried it. No, not yet. We're not there yet. Then the third case is the case where phi 1 is larger than 1. And this tells us what? Well, it tells us that we could do the same thing as before, but we're going to have a problem, because xt will indeed be equal to this. But because phi 1 is larger than infinity, this is going to go nowhere. Well, this goes to infinity, or it doesn't converge. Maybe I should write not convergent. Therefore, we have a problem. But we can always do this. So if our equation is xt is phi 1 xt minus 1 plus zt, then we can always do this. So I divide by phi 1 on either side. I keep the xt minus 1 on this side. I move this guy here, and I'm left with that equation, which I can rewrite perhaps in a more natural way like this. Okay, and this gives us what? Well, it gives us an equation of the form rho times xt plus some other noise, which I will call zt prime or tilde. What did I put? I put prime. So here what do we have? We have rho is 1 over phi 1. I hope I didn't make a mistake. No. And zt prime is a white noise sequence like that. Zt prime, which is this guy, minus 1 over phi 1 zt, which is a white noise sequence. We have not changed anything in the structure of the sequence except its variance. So this would be the variance, sigma squared over phi 1 squared. The problem with this is that, well, by the same argument as in point 1, again, when I say this, please check it. Make sure you agree, that you understand what I mean. We get that xt minus 1 is, so we get that there is a neat solution to this equation here. And this solution is what? Well, xt minus 1 will be the sum, which is here, rho to the power j z prime t plus j, and this again is in L2, so it's the limit of the series in L2, and that's a nice stationary solution. But it's got a problem. It depends on the future noise. Zt plus 1, Zt plus 2, and so on, which is not good. Well, I put quotes around it. So far everything is clear and you agree? Okay, so this leads us to section 3.3. How did I write that? Okay, section 3.3, causality. Now we have a definition. (3.8), where we say that xt is causal with respect to some process yt if there exists a function f such that xt is a function of yt but only in the past. For all t. We had a proposition which is, well, which is just basically a restatement of what we already said, so I'm not going to go into this. And then we had the definition of a causal ARMA process. So definition 3.11. xt is so if xt is ARMA, so an ARMA PQ process xt is causal with respect to its noise. Maybe that's not very well written. So an ARMA process xt, which is solution to phi of b xt is equal to theta of b zt. Well, that guy is causal with respect to zt if there exists a sequence of coefficients psi j such that, well, first of all, we have a condition which will play a role in the rest of the course. So it's a summability condition, and what? Well, and xt is a linear process in terms of the zt's. So that means that xt can be written as this one. And we will have to clarify exactly what we mean by this summation. We will do that later on. And this is called the causal representation of xt. Okay. Now I abandoned you on this example.
Excuse me?
Yes?
Just here, I wondered in the definition, is there we use absolute summability of the coefficients. Why not square summability? Because in chapter 2 we used square summability for convergence in L2.
Yeah, because
is there a major difference?
Yes, there is a difference which will be clarified in section 3.4, I think. Yeah. So if you have square summability here, then you have convergence in L2 of this sequence. If we impose the stronger condition that we have absolute summability here, then we have a bit more on the convergence here, and that's what we're going to want. So if you want a little spoiler, it's what's discussed in proposition 3.13, whose proof we already, which we already discussed actually last week. Okay?
Yeah. So in fact it's a stronger condition in general.
Yeah.
Absolute. Okay.
Yeah, so for example, think a good example to keep in mind is sum over 1 over n squared is finite, but sum over 1 over n is not. Okay? So when we're asking this, we're asking basically more than 1 over n's. It has to go a bit faster to 0. But that's the condition that we're going to prefer for the sequence, because it gives us a bit more. Now, let's see. Has anybody here tried to do the computations in example 3.12? They're not easy.
I tried.
Did you get them?
Yeah, in the end I got them. Took some time, but...
Yeah, it's not easy. Anybody else? I guess not. You should. I mean, it's... Otherwise, you won't enjoy the course. I mean, it's in these exercises that the fun is to get. So let's do this example in detail now. Well, Clara, seeing that you're the only one who tried, if you have an alternative way of doing it, please say so. Well, give us your alternative. So we start with this, and we take phi1 larger than 1. So we have now a stationary solution, which is so we know that there's a problem because of the fact that this coefficient is larger than 1, and we know that the only stationary solution is this guy. I think there's no minus sign though. No, there is no minus sign. Which is not called, it's ZT plus J, sorry, which is not causal. Which is not causal with respect to its noise ZT, but we can make it causal with respect to an alternative ZT. And how do we do this? Well, we do it as follows. We define ZT tilde, which is this guy, and the claim I make is that ZT tilde will be white noise with respect, with mean 0 and with variance sigma squared over phi 1 squared. So what? Sorry, I'm not doing this well. We define that guy and then that's my claim. That guy is like this, and what? And well, xt is 1 over phi 1 times xt minus 1 plus zt tilde, so that xt will be causal with respect to zt tilde, simply because now we are in a situation which we have already seen, in which the coefficient is now less than 1. So to prove the claim, it's quite a neat exercise. So that would be my claim star. We need to show that it has mean 0, that it's got variance this, and that at different times the zt tildes are independent. So what? So the first thing to do is to show that yeah. So zt tilde is this guy. So he's what? He's this guy. like this. Minus this guy. Okay, I think I'm making a mistake. So this gives us what? Well, it gives us that guy can stay. This will give me what? Well, when j is equal to 1, I have zt. So I have 1 over phi 1 squared zt. And then I will have minus 1 over phi 1. I'll take one more, like this. And I sum for j going from 2 to infinity, phi 1 minus j minus 1. I think this is correct. Let's just quickly check. If j is equal to 1, I have zt phi 1, so this is correct. And then if j, we go for j going from 2 to infinity, and that's correct, and I have a phi 1 to the power 1. Yeah, so this seems correct. But of course this guy here is equal to this. So this leaves me with what? It leaves me with minus 1 over phi 1 squared times zt plus 1 minus 1 over phi 1 squared times the sum here.
Professor,
Yeah.
can I ask a question?
Oh yeah, of course.
Yes. When you say 1 over phi 1 square, the second one, it is not 1 over phi 1? Why it is phi 1 square?
This one here?
Yes.
Because I wanted to make a j minus 1 appear here.
Okay.
So
Okay, I see.
if I do it a little less fast, I have minus j plus 1, and here I have phi 1 times 1 over phi 1. So that this guy cancels out with this guy, and I'm okay.
Okay, thank you.
Sorry, I just think I had the opposite signs. I'm not sure where it went.
It's because I see that in my slides I wrote xt is minus this sum here, but I have the impression that it's in fact xt is equal to plus this sum here. If I go back to what I did here, xt is in fact the sum plus the sum, not minus the sum. So I don't have a minus sign here.
But the z prime is defined as minus rho z normal.
Okay, thank you.
Think.
Okay, z prime here. Okay, that's okay. Thank you. Yeah, because last night when I was preparing, I had a minus sign as well. So there's a minus sign here, and therefore there's a minus sign here, a plus sign here, minus sign, plus, plus. And we're happy, so that now we have the same thing as in the slides. That's better. Like this. Okay.
Sorry, maybe just one more question.
Yeah.
Because I also had somewhere a term with 1 over phi 1 n to the power n zt plus n, but the limit with n to going to infinity.
Yeah, I'm working in L2 here, so I'm writing this as the limit already. So I'm cheating a bit.
Yeah, no, wait. So apart from this term, I had one additional term. Yeah, because when I wrote it as a limit and not as a sum, one went from j is equal to 1 to n minus 1, and the other went to n, so there was like one thing that didn't cancel out. But
maybe you can show me afterwards, but it should go to 0. I mean, this is in the limit, correct?
yeah, well, that's what I wanted to ask, because this term is something, but it's a random variable, but since it's 1 over phi n to the power n, it should go to 0.
Yeah.
Probably almost surely then.
Exactly. It will go to 0 almost surely.
Yeah, and then
but yeah, so
we can leave it out then.
Not really. I mean, if you write in terms for fixed n, then you keep it, but it will disappear at the limit. So here I am cheating when I write this like this. Marianne, you had a question, or did you already ask your question? Okay. And now that we have this, then it's quite easy to simply use the same arguments as before to say that expectation of this guy here is going to be 0 plus minus times 0, which is 0. And again here, so here I'm speaking about an L2 limit, and here again I'm taking the L2 limit and I'm exchanging integrals and limits thanks to proposition, I forget which number. And if I look at the expectation of zt tilde squared, I have what? Well, I have this, so I have phi 1 minus 2 zt squared plus if you authorize me, I'll just put it in the same way as it's in the slides. So I'd exchange these two guys like that, and I put a plus sign here. So then I have this times this no, sorry, it's not a minus j, it's a plus j here. Squared, and then I have twice this. So now I'm just working out the square. So it's the square of that plus that, so it's going to be that squared plus twice the cross product. So it gives me exactly this expression here. And now I just work things out. So we recall that zt is white noise with mean 0 and variance sigma squared. So this will give me the first term here, let's say in orange, will give me sigma squared over phi 1 to the power 4. The second term will give me, well, that doesn't move. And this gives me what? Well, only because zt is white noise, only the squares will count. All the cross products will have a 0 correlation. And again, I'm cheating by taking, well, I'm switching limits and integrals thanks to the so the proposition in chapter 2. So I'm left with sum for j going from 1 to infinity of phi 1 to the power minus 2j times sigma squared, and plus what? Well, plus here I have zt, and all these are dependent on the future, so all these guys are uncorrelated with this guy, so this gives me 0. And this sum here, I know that it's equal to 1 over 1 minus phi 1 minus 2. Minus 1, why minus 1? Because the sum starts at 1, so I have to remove the first term here. And now it's just a matter of doing this properly. So I have the sigma squared, which I take out. I have 1 over phi 1 to the power 4. I have what? I have what do I have? I have phi 1 to the power minus 2 minus 1 squared. This guy here is then equal to 1 minus 1 plus, so it gives me this. I think that's okay. So I have phi 1 minus 2 divided by 1 minus phi 1 minus 2. And one of these guys will cancel out one of these guys. Well, with that guy. So I'm left with this. So what's that? It's going to give me, at the bottom I have phi 1 squared, and at the top I have 1 minus 1 over phi 1 squared. And I think I'm nearly there. I got this. This is long. Yay! Okay, and then I'm left with sigma squared over phi 1 squared. Okay, that was long. You see the idea? Clara, did you not have troubles with your limits if you kept the limits explicitly?
No, I didn't think so, because well, I changed at some point the limits with the expectation, and then I had 1 over phi n to the power n, so it went away.
Okay. Guys, it's already 3:15. I will leave you the next part as an exercise because it's still quite long. Can maybe show you? I have 1.5 pages with this. And I'm guessing it's not very useful for you to see me do these computations. So I let you as an exercise the fact to compute that expectation of zt tilde times zt plus h tilde. Well, you just replace by what you need to replace, and then you be courageous. So I'll put 3 dots followed by 3 dots followed by 3 dots. And somehow miraculously everything cancels out, and it's quite, I mean, I like this. I like when things happen nicely. And then you're left with 0. I didn't see any obvious argument why it would be 0. I mean, it's just, for me, it's just computations. Okay. So this again, this kind of stuff is typically a very, I mean, for me, it's a very nice exam question because I don't think you can find that online. And if you do, well, then it means you've gone through all the books, which is a very good sign. So that would be a nice exam question. And another nice exam question is where? Is, for example, give a very detailed proof of this, that could be a nice exam question, that kind of stuff. Okay, so we'll have a break, but before we have the break, I'd like to move on a little bit more because I was not intending for this to take so long. So we now move to the section 3.4, conditions of so maybe if you're curious, it's not my example. I took that example. Where is it? It comes from Neusser. Where was it? You know where to find the books, don't you? I mean, you see the books on the. I think they're on the UV. I forget now, but they're also available on Teams, so you know where to find those books. I'm guessing you do, which is so if you go and see the book by Neusser, page chapter 2.3 and page 33. That's where you'll find. That's where I found that example, which I found pretty cool. Now, conditions of existence of causal and stationary solutions. So before we go into this, we'll have a break. But before we have the break, here is some information that you have to know. So I'm guessing most of you know this or have heard of this. But if you have never heard of it, well, please learn it because it's really useful. And whenever you do this kind of maths, you will see these theorems appear. So either you know this. So I won't ask an exam question about this, of course not. It's too mathematical. But you have to know these results, or at least know where to find them on Wikipedia. Although the Wikipedia page is not so clear on this. So the question is the following. If we have xn which converges in some sense to x, does this imply that the mean of xn converges to the mean of x? And the answer is it depends. So what we have already seen, so that's proposition 2.4 seemingly, that if xn is in L2, if yn is in L2, so we're working the Hilbert space L2 equipped with the L2 norm, which we know to be nicely well behaved. This inner product is continuous, and we know that if we have sequences which converge in L2 to some x and to some y, then what? Then the expectation of xn yn converges to expectation of xy, and we know that the expectation of xn squared converges to expectation of x squared. Okay, but in general, things are a bit more tricky. I guess it's a good time to have a short break. It's been a long speaking time for me. So let's have a break now, and we'll start again in. So it's now 3:21. Let's say we start again at 3:40. Is that okay? I'll start a new video. Okay for everybody? Okay,
Yes.
I guess it is. So see you in well, a big quarter of an hour.